Hi, my name is Bob Westervelt, and this is the first of the Wednesday night seminars in the physics department. Each Wednesday night at 7:30, one of the faculty members in the department will be talking about their own research. We encourage everyone to ask questions. This will be on Zoom, and so the way to do that is to raise your hand by punching reactions at the bottom of the page here, and you'll see a hand raise symbol. And by all means, ask questions while they're talking so that we can get a discussion going back and forth. The talks will go for about 30 minutes with additional questions and answers at the end. And today we have Julia Mundy. Harvard, we were lucky to manage to get Julie to accept our offer and to come here. She was a Harvard undergraduate and then went to Cornell, where she did some really sort of groundbreaking work in oxide, the growth and analysis of oxide materials, I think part of which she'll talk about today. Then did a postdoc at Berkeley and then came to Harvard. Julia, take over. I think it should work.
Okay, thank you, Bob, for the introduction. And I guess for the few of you that joined after we started, I have to mention that it's very special for me to be here giving this talk with Bob, because he was the first one that introduced me to the concept of MBE technologies in his course. So it's a fun thing. So today I want to tell you about what I think is really the most exquisite way to control materials at the level of atoms. And so I want to show you how we can synthesize new materials atom by atom by atom, but also how we can think about further tinkering with structural distortions and displacements in these atoms at the picometer scale. So I'm showing an example here, which I know that you read about in the paper in advance for this, which is showing a ferroelectric material where you can see this up, down, down displacement of the atoms. And so that gives rise to a ferroelectric polarization. But in this material, what was quite exciting was that little picometer distortion strongly modified the magnetic properties in the adjacent layer. So really thinking about how we can tinker with atoms allowed us to design new materials that had not been made before. And I'll say also, you can also raise your hand, but you can also just interrupt me, because sometimes on Zoom, I don't see the hand thing, and then but please, anytime. Okay, so really maybe the biggest message that I want to give you today, if you take one thing away from this, is that materials are really exciting. And in my opinion, materials are the conduit to new physics. So a lot of times in undergraduate, we think about kind of a paradigm for science or a paradigm for physics, where we think about, we sit down really hard, we come up with a theory, we have this brilliant theory, this inspiration, these ideas, and then we go in the lab. And inside the lab, we verify the theory or prove it wrong or what have you, but that there's kind of this life cycle of physics that, first comes the theory and then comes the follow-up experiment. And so certainly that can happen. And sometimes science does proceed in that way, including in my field. But several times, it really does not. And it's really inverted, where not only the experiments can kind of lead the day, but even within experiments, the kind of construction of new materials can be really what excites the community. And so I'm showing two examples on this title slide, neither of which are specifically important, but both are really exemplars of this. So one is this fractional quantum Hall states. And one thing I find exciting is that these are MBE grown films. And so this is a phenomena that was discovered in the 1980s, where they found that the Hall conduction that you get is quantized to these precise plateaus of fractional values at low temperatures. This is something that really was not theorized before it was discovered, and really was something that was very revolutionary in physics. That really led to a number of different discussions and investigations that actually continue to this day. The other example, perhaps, of this phenomena was the high TC superconductivity. So once again, from the late 80s, before high TC superconductors were discovered, almost all kind of known superconductors were expected to be this BCS superconductor. And that was, something, a Nobel Prize had been given 3 decades earlier. That was something that was kind of thought to be understood and solved in physics. And so not only the fact that materials could superconduct at high temperatures, but specifically that they could really arise out of this system that's had strong electron-electron repulsion, really blew apart the field and also has motivated many of the work that's continued to this day. So I just give these two as examples, not for the specific physics in these two different compounds, if you're not versed in condensed matter, but really just to motivate, hopefully, that, it was the construction of these materials, and in particular for the fractional quantum Hall effect, the ability to make really highly pure, low defect materials that really provided a platform that allowed this kind of new physics field to evolve. And so, this is something, both of these studies are really exciting to me today, because I use MBE, like the fractional quantum for different materials, but the very same techniques. And I grow oxide materials like the cuprates and also study superconductivity. So both of these things are things that really continue to motivate me today, but really just at the high level where it was the material, the existence of the material and the measurement that blew things apart, and all the theoretical understanding came later. Okay. Okay, so the specific materials that I'm interested in are these complex oxide materials. And these are these various, we call them quantum materials, but these various different materials that are based on kind of this canonical complex oxide AbO3 structure. And the exciting thing about these materials from a physics standpoint is that the energy scales for the electron repulsion and the electron kinetic energy are about the same in these materials. And so because you have these kind of similar kind of energetic scales, you get these highly sensitive ground states, these highly sensitive quantum states that are extremely perceptible to small perturbations. And also whereby you can stabilize this really wide range of physical phenomena. So these oxide materials that I'm interested in display a whole range of states, from conductivity to superconductivity, dielectrics, ferromagnetism, as well as some more recent studies in some topological phases. And I just, yeah, go ahead.
Sorry, yeah, hopefully I can ask, like,
Yeah,
when you
please.
say like these ground states are like sensitive to small like perturbations, like I don't know, what's an example of that, or like what more specifically what kind of sensitivity are you talking about?
Yeah, so what I'm saying is that these ground states are, first of all, very temperature dependent. They can be very susceptible to different magnetic fields, but also the materials that are, for example, superconductors versus ferroelectrics, et cetera, are sometimes not that far off in the chemical composition. So slightly different atomic structures, slightly different atomic spacing, slightly different chemical compositions can really kind of tune across all of these range of properties. And I'll show you some examples on the next few slides, but really just they're not kind of all metals or something like that, but that you get these states where you can have a really wide range of phenomena where you feel like you did something very minor to change the material. Yeah, that's a good question. Yeah, and so, I guess the thing I just also want to highlight, we're talking about why we got into various fields and what have you. One thing I just wanted to say is that, this work in this field, I think, is kind of driven by two parallel questions. One is, of course, we want to understand these phenomena and understand the physics of these systems better. However, there's also kind of an interest in these materials from a technological standpoint or for a variety of different applications. So, for example, with superconductivity, we want to understand superconductivity better. There's still open questions in superconductivity, but we also want to discover a material with higher temperature superconductivity or higher critical currents or what have you for various applications. So this work is really kind of a toggling back and forth between trying to do fundamental physics, but also kind of caring about trying to engineer the properties of these materials and to discover new materials with enhanced properties. Yeah, and so I don't want to necessarily go through all of these various different things, But I'll just mention at a very high level that the types of materials that I'm interested in, as I mentioned, are of use and are of application for a wide range of different next generation applications, many of which overlapping with kind of energy efficient devices or energy applications. So both kind of explicit energy storage and refrigeration and what have you, power lines, what have you, but also in thinking about things like how can we make our computers consume less electricity? So how can we think about storage devices, memory storage in your computer, in your phone or whatever that uses a fraction of the power consumption of your current devices. And so, you know, this is also motivated really just by reducing, in those cases, our kind of global energy budget and our dependence on energy for those various applications. So the material system that most of our work is in this transition metal oxide family. So this is this canonical AbO3 structure, where in the crystal structure, we have this A site cation that's shown in yellow, and a B site cation that's in here in blue, that's surrounded by a cage of 6 oxygen atoms in an oxygen octahedra. And we can see on this periodic table that almost every element in the periodic table can be found in this perovskite oxide structure. So I'll say if you want to see the original perovskite, it's a rock, it's calcium titanate, and there's actually some of it in the Natural History Museum across the street from where I'm sitting right now. So if you want to see the original perovskite, you can go look at the rock. That's calcium titanate. But many other elements can be found in this crystal structure, kind of in this same crystal family. And so the idea here is that there's this wide range of elements, which gives rise to this enormous number of electronic and magnetic properties, as I mentioned on the previous slide. But the idea is that there's this common structural motif. So as you're sort of putting in various different elements into this crystal structure, the physical spacing of the atoms actually changes very little. So the physical spacing in this family might range from, 3.7 angstroms to 4.1 angstroms, but it's really, small percentages changes as you're putting in various different elements. And so that allows you to think about not only how you can make these single phase materials and discover all these various different properties, but also how you can stack materials on top of each other in a kind of coherent stack without any kind of disorder or defects or what have you, and think about that stacking and those layers and those interfaces as a platform to study new emergent phenomena as well. And so I should say that these structures can have distortions or deformations, so they're not all kind of this perfect isostructural cube, but kind of have this same kind of overall kind of oxygen connectivity and architecture. And so, Cleach, I think this is the better answer to your question maybe here on this slide. So I want to give one example. So this is kind of looking at a bulk crystal, so a single hunk of a material. And this is this cuprate material that I mentioned at the beginning. And none of this is very important, but the big idea here is that this is a temperature axis on the y-axis, and the x-axis is doping. So what they're doing is they're putting in one cation for another, a yttrium for a barium or something, where they have a slightly different electron count, a slightly different valence electron count, and then you're kind of changing the number of electrons that are going into the system. And so you can change the number of electrons by a few percent, this cuprates, and you see that you go all the way over from an insulating phase that's antiferromagnetic to a superconductor, to some metallic phases, what have you. So, there's these, as I mentioned, these very sensitive ground states where you're changing 1 or 2% compositions, and you're going from an insulator to a metal, or a metal to a superconductor as a function of temperature as well. So within bulk crystals, kind of single phase bulk crystals, that's the main axis that one has with the structure, is this cation substitution. So putting in one element on the periodic table for another. But when we start to think about thin films, We can think about layering materials on top of each other. And we have a whole playground of kind of additional degrees of freedom and ways to think about optimizing properties, where we can think about kind of that interface between the two materials as being the location that the new physics might happen. And so there's a number of different kind of knobs that you can play with there. You can think about reducing the dimensionality of the system. If you've followed maybe some of the work in condensed matter, you've heard of graphene. And graphene is a single monolayer, a single sheet of graphite. And the properties of graphite are quite distinct from that of graphene. So going from a bulk material down to a layer dramatically changes the properties. We can think about doing that with a whole number of materials where we reduce the dimensionality and kind of go from something that's a 3D structure and bring it down to the 2D limit. We can also think about kind of broken symmetries. Now you kind of break that interfacial, that kind of mirror plane, that symmetry in the crystal when you have two different materials. We can think about chemical potential offsets. So, kind of thinking about two materials with very different chemical potentials and kind of using that interface as a way to move electrons from one material to another. We can think about epitaxial strain. So we can think about a material that has a lattice constant where the atoms are spaced maybe 3.9 angstroms, and then we put a material on top where it wants to be 3.8, but it's going to stretch to kind of follow that underlying template that we deposited on. And we could think about kind of changing lattice constants by 5 or maybe even 10%. And so this is actually quite profound. If I took one of these bulk crystals, they're ceramics. If I took one of them and tried to pull on it and stretch it by 10%, it would just shatter. I mean, you would make much less than 1% changes before it would shatter. So you can think about in these thin film limits, really distorting something and pulling it apart, just kind of physically separating the atoms, which then could, very profoundly change, kind of if there's a spin on one atom and a spin on one atom, kind of how they overlap and how they interact with each other. We can also think about these lattice distortions, not just changing the lattice constants, but if we look at one material that kind of has that kind of deformation of the lattice, a different one that doesn't, we can try to kind of at the more micro scale, think about how we tinker with the lattice. We can also think about kind of a number of things, proximity to functional phases. If I put one material that's a magnet next to one material that's a conductor, what happens at the interface, or kind of think about trying to couple different materials' properties to each other just by proximity. And then the last thing that a lot of my research has focused on is making materials that just aren't even stable. So if you tried to make them by some, put all the atoms together and cook it chemistry technique, you wouldn't even be able to make a material. But by this precise layering technique, we're able to control this and to engineer it. A lot of stuff on that slide, so I can answer questions if they're. Yes, Bob. Oh, I think you're muted though. Oh.
Hi, does it
Okay.
blow up while you're making it, or do you get to wait a month or a year, or how long do you have?
Depends on the material. Yeah. So some of the materials are air stable, some are not. So it really just depends on the specific compound, but some of them can be around for years afterwards. But some of them, yes, I mean, in this limit or something that we did, it's not, it is sensitive to air, although some bulk crystals are air sensitive too. So, but we have more surface area, so I guess it's more catastrophic for us. So,
okay.
Yeah.
Other questions? Okay, go ahead.
So I'll say that this process of combining materials at the atomic layer level is exceedingly easy to do in PowerPoint, but way harder to do in the lab. So this is some PowerPoint, cartoon thing where you could stick atoms on top of each other. But I want to show you can actually do it in a research lab as well. So this is one of the materials I'll show you on the next slide. But each of these dots that you see on this picture is a single atomic column. So this is a cross-sectional view of one of the materials that we have synthesized. And in this particular compound, we started off with our substrate that happens to be strontium titanate, and then we've synthesized this material in this 3-6-3-6 kind of atomic layer pattern. And I'll show you on the next slide why we were interested in that. But you can see that we have, both quite high levels of control over this material. We can put down 6 layers. We can do it again and again and again. But also, this is a real data. This is an electron microscopy image of this material. So we can put the atoms where we want them, but we can actually see the atoms and take pictures of the atoms and see that they went where we thought they went in kind of other aspects of the electronic structure at the atomic level. So, yeah. And I think this is really cool. I think like seeing atoms is really amazing. And so many people through so many, generations of science never got to see atoms. So I think it's really cool to be able to go in the lab and see atoms. So, okay. So I just want to show you with this project, maybe just like one little vignette about how things can change at the atomic layer. So how if we made something that was 6-3 versus 4-2 or something like that, how this kind of atom level control over things like actually can change the properties of the system. And that can be a really powerful tuning knob at these length scales. Okay, so this is just one kind of short vignette of a project I was involved in. And so this project involved putting together one of these oxide materials, which was lanthanum manganite, so lanthanum manganese oxide, which is a insulator for anyone who's done solid state, a Mott insulator, but then is also anti-ferromagnetic. So there's spins on each of the sites, but they go up, down, up, down, up, down, and there's no kind of net magnetization in the system. We interfaced it with lanthanum strontium manganese oxide, which is also an anti-ferromagnetic material, also an insulator. It's a band insulator, so it has 2 N electrons for anyone like the full band. The Mott insulator has N electrons, so it should be a metal, but due to some correlations becomes an insulator. First of all, if you put them together in this 2-to-1 ratio, so 2/3 of your sites are lanthanum, 1/3 of your sites are strontium, you get a ferromagnetic metal. So you get a metal from 2 insulators at the atom, kind of scrambling up the material, and you also get something that's magnetic, ferromagnetic, like a refrigerator magnet. So that's if you just kind of scramble all the atoms together. So what we were interested in is what happens when you, instead of scrambling all the atoms together, you start with these end member compounds and you bring them together at the atom level. So kind of what is the length scales that you get the kind of scrambled together kind of mixture properties, and where do you see it start to phase segregate out into the kind of 2 parent phase compounds? So these are superlattices of these materials. So I'm showing lanthanum in turquoise and manganese in red. And we went from a 2-1 to a 4-2 to a 6-3. So basically we're just tuning that periodicity knob. So we kept that 2-to-1 ratio, but we're just changing the spacing by single atomic layers in each unit. And so what we found is that when you go to this very thin film limit, the 1 or the 4-2, you get a ferromagnetic metal, which is maybe not so surprising because maybe that kind of behaves like the solution one, kind of that end member compound. But what was very puzzling was that we got a ferromagnetic insulator state when we went to this 1 unit cell change. So going from 4-2 to 6-3 changes it dramatically from a metal to an insulator, but it remains ferromagnetic. So it kind of doesn't adopt either the end member endpoint compounds or the solid solution compounds, but some kind of permutation and mixture of the middle. And so that was quite puzzling because theoretically we would expect kind of at those interfaces where those materials meet, it should always be metallic because at that interface, it should kind of always look like that solid solution mixture-y thing in the middle. And so I actually want to save this type of thing for Jenny Hoffman's talk in a few slides, a few weeks. This is angle resolve photoemission spectroscopy, but it's a measure of the band structure of these materials, where we were able to kind of peer into them and see what happens to the electrons in these materials and why we get this insulating state as opposed to the metals for these various different layers. So Jenny, I think, is going to give a whole half an hour on band structures and a complementary technique for measuring those. But I just want to give a pitch for her talk, that we're not just kind of mixing atoms together and sometimes it's a metal, sometimes it's an insulator, but we're really able to peer below the surface and see what the electrons are doing. And from that, really be able to understand kind of the underlying physics of these compounds. Okay, so just to kind of give a high level, our goal is to, synthesize these materials with atomic precision, to be able to find where the atoms go with picometer precision. Then to be able to kind of probe those macroscopic, is it a metal, is it an insulator, is it a magnet or not, properties. And then ideally to be able to kind of directly look at the microscopic underpinnings of these behaviors. So not just to kind of mix things together and see what happens, but to really be able to understand, when I layer these materials, how do the electrons interact, how do they behave, and how does that give rise to this kind of global behavior that we observe in this material. Okay. Yeah, so I guess the last thing I just wanted to say was maybe to show you a little bit about how this just works in the lab, which is to say how we layer these materials. So what we do is we have these various, what we call effusion cells. So we have single elemental effusion cells, so lanthanum or manganese or strontium or what have you. And then we heat them up so that we have thermal evaporation. So these atoms, we're just thermally evaporating them, just like a puddle evaporates. But the kind of precise thing about MBE is that we can do this with incredible stability and kind of long-term stability and kind of controlled flux of this atom. And then you can see here that we put our substrate in this middle spot that we heat up, and then we're opening and closing these shutters that are allowing us to open it for the precise amount of time it takes, one layer of atoms to deposit. Then we can close it, then we can open up another one or what have you. So it's kind of akin to atomic spray painting, where we have these spray cans that are individual atomic sources, but that we can spray them onto the surface and do this where we're opening, closing, and allowing us to kind of build up monolayer by monolayer. And I'll say that there's, I think in my count, 4 Nobel Prizes that have been awarded to date for MBE. Including the fractional quantum Hall effect. It had a really important role in giant magnetoresistance. Blue LEDs are made by MBE, so that's a very common kind of commercial process that just won the Nobel Prize in 2014. So a really versatile technique for a lot of materials, a small subset of which we work on. Yeah, and I'll just show you, this is how it actually works in our lab. So we have 2 such of these chambers where we can evaporate the atoms in these elemental effusion cells, and then a lot of apparatus to monitor things in situ so that we know we're making what we think we're making, as well as, to kind of be able to couple that to other just types of measurement technologies. Yeah, so I guess, Bob, I think I've already spoken for half an hour. So I did prepare like a whole lot of slides about various different projects, but I don't know if the students have questions, because, just kind of with this overview level, or if there's, anything else. I can keep talking all day, but I just wanted to pause if there's things that people have questions on and respect everyone's time, but I think I am just at a half an hour now.
No, I think it was great. I think the high level overview is good. And maybe it's a good time now to ask questions. I've tried to prompt them to think of good, hard questions to ask you. So
oh, shoot.
See what,
I was wondering, how much are you constrained by like the interactions of the atoms? Like, I know in the paper that the Physics 95 students read, you had like the rumpling.
Yes.
And how much rumple, I guess, could you get in that sense? Or I guess in what you showed, how close or can you put the atoms that you were depositing.
Yeah, so I guess, yeah, you're looking at like these pictures right here or something like that. Yeah. I guess there's sort of two things that we can control with the rumpling. The atom spacing in this compound, we can impact it a little bit with the underlying substrate, but materials do have some equilibrium bond length, covalent bonding. So we can't make kind of, I can't separate the atoms 5 meters from each other or even like 5 angstroms. I mean, they're kind of fixed to some kind of rough length scale. And so, most of these atoms are about 2 angstroms apart or something like that from their nearest neighbor. Here, what we were able to do with the rumpling is we were able to make a series of compounds where we were changing the layering, and kind of this end member compound, the atom displacements are about 40 picometers, and they don't exist in the opposite end. If we go to the other end of the distortions, it's 0. So by making kind of these superlattice structures where we layer the materials atom by atom, we were able to interpolate between the kind of rumpling of 40 picometers and, not having some of those distortions. So, we do have some limits on what we can do, but we did find, at least in this system, that it really was a very powerful probe. A lot of physics happened differently with the various different levels of rumpling.
Other questions?
Yeah, I have a question about like, it came to mind when you were presenting or showing the like AB03, the kind of like general template for like a lot of these materials. And I guess like, how does one sort of decide, like, I could pick any combination of like all of these sort of elements here. And I feel there's like, I have 2 questions, one of which is like, oh, are people really exploring all the different like possible combinations? And like, if not, then what motivates why one might theoretically or empirically believe one is like better or interesting than another?
Yeah. I have to say this is a great question, and also one I got on my faculty interview by all the professors that were interviewing me. So this is the question. I mean, this is sort of the $1 million question in the field, is how do we decide which materials to grow? So there's a lot of different motivations that we have. Sometimes somebody has done another experiment in bulk crystals or a different type of thin film synthesis technique, and they got some promising results, but they kind of hit a wall in terms of what their technique was capable of. So we have kind of the ability to layer materials and to have kind of precision that other techniques do not have. So sometimes it's like there's a trend and you really want to be here and they just stop here. But you're like, if I could extrapolate that line, boom, I'll be right there. So sometimes, we just have kind of ideas from other experiments that, guide us. Sometimes we have fundamental questions or either theoretically motivated or from ourselves, what would happen if we put a topological insulator on a magnet? And maybe there's not a precise theory that says put this compound with that compound, but we're kind of thinking about if we want to marry 2 materials that have the types of dissimilar properties, but ones we think may interact at an interface or something like that. And then I'll say also, I think the research is really fun. And sometimes we also get surprises. I wouldn't say it's our strategy to hope for serendipity and hope for cool things to happen. But one of the really exciting things is being able to make compounds and then to measure what you do get. And sometimes there's projects that kind of evolve organically out of that, where we notice something cool and then we chase it. So I can just be really frank about this. This material, this lutetium ferrite 113, was an impurity phase of my colleague's attempt to grow the lutetium, the one in blue, the lutetium ferrite 124. And so we noticed that some of his samples were kind of crummy, but the crummy ones were much more magnetic than the not crummy ones. And so then, we did TM and we tried to figure out, okay, what are those impurity phases? How do we isolate it? Which we did. We isolated the lutetium ferrite 113 compound, and we were really proud of ourselves. This is going to be really amazing. And then it was non-magnetic. It's anti-ferromagnetic, but at low temperatures. And then we realized, okay, maybe it's not the fact that we have those impurity phases, but it's the kind of interaction between that impurity phase and the other parent phase that we really need the two materials together to get the phenomena. So that was something that, we kind of just noticed something when we were trying to grow one of the materials, but because we had the TEM, because we had all these other techniques, we weren't just kind of blindly seeing that it was getting more magnetic, but we could kind of go in and pin down what it was and try to isolate it and chase it and kind of follow along that pathway. So this was a project that really came out of serendipity, but other ones have more kind of intelligent design at the very onset. So, yeah.
There's a question from Edgerman, Boston.
Yeah.
Correct me if I'm saying it wrong. It says, sorry, I can't speak the way it's hooked up, but the question, how much is the work that your group does is instrument design and manipulation versus modeling, theorizing, experimental analysis?
Yes. Okay. So I guess instrument design, these are commercial instruments because we're kind of using them an off-label purpose for the oxides, but they are used in a lot of semiconductor materials. So I wouldn't say it's so much instrument design like some of my colleagues do, but I would say it's instrument maintenance is what we maybe spend our time on the equipment. So the joke is that the letters MBE stands for molecular beam epitaxy, but the joke is that it stands for mostly broken equipment. So there's a lot of time that's spent just on fixing the equipment and keeping it online and maintaining it. So I think that, by the time the students graduate, they may have replaced every screw on the system through various projects or another. It comes working, but then keeping it working is the piece. So my group doesn't design these so much. We definitely have some kind of nuanced new techniques or tools or ways of doing things. But the kind of base equipment to first order, we do purchase. And that's different than somebody like Professor Hoffman, who you'll see, who builds all of the STMs, and Professor Jacobi or some of my other colleagues who really do build custom instrumentation. Modeling, theorizing, and experimental analysis, I think it really depends on the project and the student and the time of the year and whatever. So I think that we have projects where the students will spend long periods doing mostly synthesis and thinking about their synthesis and interpreting the results. And other times that they're doing measurements on something that they may spend a lot of time doing measurements and kind of analyzing the data. So I would say on that question, it really just depends on the specific project, which sometimes is luck or sometimes is the student personality and kind of which aspect they like and seek out.
Oh, thank you. Other questions?
I have a question about the read system. Or the MBE system. I think there's a slide, you have a diagram.
Yeah.
Showing the different parts.
Yeah.
So I understand the read camera is to kind of see if there's like the layer has been deposited precisely. Mm-hmm. Do you have to kind of continuously keep watching the camera throughout the growth or check after each layer of deposition?
Yeah. So we watch it continuously. So we can see, as you mentioned, Sam, like we can see that the layer's been deposited, or if something wacky is happening, it's not going down smooth, it's kind of crumpling up into a ball or something like that. But usually we watch, depends on the project. I mean, sometimes, if we're just making a single material, not all these interfaces, maybe we don't care quite so much about the growth rate, but we usually keep that running pretty much the whole time. So,
yeah. Any more questions? Last question.
I have a question about the reduced dimensionality you mentioned, I think, in the beginning. I was just wondering physically, why is it that a monolayer has different or interesting properties than something with greater dimensionality?
Yeah, so I mean, in the case of graphene, you have, I know this is Elizabeth, and so we did this problem in physics 195, but you have the bonding of the monolayer at that point, the pi-pi bonds that give you kind of this 2D electron structure. So the electrons kind of live in 2D. You have a density of states that depends on that, and you have a band structure that's precisely due to the 2D. If you maybe start to bond it to a third layer, then you have interactions in the opposite layer as well, additional bonding or what have you, depending on what's going on. And then at that level, things can just change the band structure dramatically, and then it can change the properties. So, yeah. Not every material behaves differently as a 2D layer than in the bulk material. And also, sometimes we're looking for new physics in a 2D layer, Other times we're really hoping that the 2D layer looks like the big thing because we want to scale it down for some device or some interface or something like that. So we're really just hoping it looks very similar when we get it thin as well. So, yeah.
I see. Thank you.
Yeah.
Okay. One last question. Okay. If not, thanks so much, Julia. It's very nice talking. I'm really envious of your animated MBE machine, which I was trying to somehow reproduce with not nearly so much success, but very nice.
Yeah, thank you all for the questions and conversation. I know it's late at night and I don't know, presets are due tomorrow and whatever. So I appreciate everyone's attention and everything. So yeah.
Okay, let me finish up by saying that next Wednesday, we're going to hear from Eric Heller. And the title of his talk is Electrons in a Sea of Vibrations. There is a world beyond phonons. And I think we did some work a while ago, which is becoming quite hot again, which is branches of sound in the ocean. It turns out that sounds that are generated half a world away actually focus into beams and make their way to San Diego, the surfers there. And so he'll show you how that works, and we'll talk about that the Monday before. Okay, thank you all so much, and we'll close up the show.